Hello, class. We are going to look at Millikan's oil drop experiment. And so there are several things that we'll look at inside of this section. You'll see that we have fundamental particles and interactions resource. This is a great resource when it comes to fundamental particles and interactions. And so basically it gets into what leptons and quarks and bosons and stuff like that. So and what they're made up of. So if you want to look at this a little bit more, I think it'll be good to check that out. And we also have another resource here that I think is quite useful. Just understanding more modern physics and nuclear interactions. And hopefully it'll come up shortly here. And that is nuclear science resource. And I'll just go to that real quick. Okay, so this is getting into nuclear science and what's happening and the models and the theories and the ideas that people think, they think things are happening a certain way, and then they have some evidence to support them. So it gets into alpha decay and beta decay and gamma decay. So you might want to look at this, take it just a quick look, but it's in your book as well. Let me see, I think that's pretty much it. Let me go back to mobile. So now we are going to get into the Millikan oil drop experiment. Before that, though, we're going to do ourselves a lecture. Let's see if I can get to that. Get to. There we go. So this needs to refresh, and I'm going to give it a little while. And I'm going to go ahead and change this to Millikan. And so there's a lot involved in this. There's not a whole bunch involved in the experiment because it's been done so many times. We have apparatus here. The gentleman who did it, Millikan, he won the Nobel Prize in Physics for this, so which is quite important. He won it in part for the quantization of electric charge. Basically, electrons are going to come in discrete packets. Or like 1, 2, 3. It's never going to be 1.5 electrons or 2.5 electrons. It doesn't work like that. Now, charge could be like that, but electrons are not. And he also won it for the photoelectric effect. He won it for both of those. So that's cool. So where I want to start is with gravitation. Oh, believe it or not. This is why we talked about gravity before. We know that we have M1 here, M2 here. We know that if we have a distance of separation between the centers, R, okay, and we're going to have some force acting back on one another, F sub G, and F sub G is just equal to the universal gravitational constant times the product of M1 and M2 over the square of the distance of separation between their centers. It's all this is Newton's universal law of gravitation. So guess what happens when we have two objects that have a charge on them? Okay, the first two objects have a mass, property of mass. The second two have the property of charge. Okay, let's just say that one is positive and the other is negative. So charges that are unalike attract one another. Charges that are alike will repel. So two negative charges are going to repel, two positive charges are going to repel as well. Okay, so the distance of separation between their centers is going to be represented by R. And the force acting on one another, I'm just going to call that F sub Q, it's going to look like so. So guess how this particular formula is going to look. Look up here. We have F sub G is equal to capital G, and this is our universal gravitational constant, times the two properties that are under consideration, which is mass. Mass gives rise to gravity, okay, divided by the distance between their centers squared. Now look at this. We have the force due to charge. We're going to need a constant in between them, a proportionality constant. We call this Coulomb's constant. It's just 1 over 4 pi epsilon, epsilon being the electric permittivity. And this is going to be Q1 times Q2 over R2. You see that symmetry there? Isn't it beautiful? Yes, it is beautiful. Must say, must say. All right, so we have those two formulas. They look very similar to one another. So the reason why I was talking to you guys about gravity was because, you know, it's very similar to, well, the way we model our electric fields is like how we model gravitational fields. And because we experience gravitational fields at this macroscopic level, you know, we can look at electric fields at the microscopic level and see how they behave. It doesn't have to be only on the microscopic level, but see how they behave.